This is the third video in a sequence of videos where I cut shapes out of sheets of paper and try to fold them up in order to make boxes with larger and larger volumes. In the first video, the first thing that I did was naturally the traditional box problem where you fold the page in this way. And I'm using the same size paper for all of the shapes that I try to do, which is 21 centimeters by 29 centimeters. And with those measurements for the original box problem, we got a maximum volume of 1,092 cubic centimeters. Then in that same video, I started trying to get creative and I folded the paper into a cylinder instead. But that was very disappointing in terms of volume because the largest volume in that case was only like 800 and something cubic centimeters, so it was a lot smaller than the traditional box. And in the second video, I tried to get even more creative by folding a cone, and throughout that whole video, I forgot to divide by 3 in the formula for the volume of a cone. So if you look at the vertical axis of this graph, it's going to look like the biggest volume is like 3,100, but it's actually not. It's just 1,030 because you have to divide by 3, which makes it close, but still not quite as big as the traditional box. So today I want to try again. This looks like the box right now, but I am not going to fold it up the same way. I am actually still going to draw a little bit more here because this time I don't intend to make the black dashed lines get together when I fold it. Instead, I want to match these two purple segments with each other so that the sides of the box will no longer be rectangles like they were before. There's going to be like this trapezoid shape. And the same thing is going to happen for the other sides of the box. This is also going to be a trapezoid. And the only wasted space will be this kite-shaped thing in all four corners. And what makes this problem interesting so that it is still worth solving even though you have already done the original box, because it's not just a repetition of the same thing, as well as choosing how far from the sides of the page the dashed lines are, which you also had to choose originally. Now you also have to choose how far from the dashed line is this triangle going. And those two things really are two independent choices from each other. So you have to choose two things, which is a feature that the original box did not have. So now let me show you how we are going to fold this box. If you want, you can cut this extra bit of paper here or just fold it inside so that the box looks a little bit prettier. But the shape of the box when seen from the side now looks like this. It's a trapezoid. I just want to make sure we put the measurements correctly on the trapezoid because the height that you see in this image from this angle is not the distance from the edge of the page to where you did the dashed line. Because when you look at it like this, you're looking at it from an angle. That distance here that you see on the side, that is the distance that you cut from the edge to the dashed line. So we are going to put the value of x not in the height of the trapezoid, but diagonally here. The height obviously depends on x, but it also depends on this angle between them here. Now the smaller base of the trapezoid is this part here. It's the length that remained between the two dashed lines. So it was the original size of the paper, 21 centimeters, minus x. So this distance here is 21 minus 2x. 21 minus 2x is also going to appear in the top here between the two red lines. But for the full length of the larger base, we need to add this little part and this little part, which are the ones that you left originally in the triangle. So the distance between the dashed line and the other point of the triangle, that is what's missing for the measurements of our trapezoid, and I'm calling y. So when you prepare the paper for folding it into this box, that's what it's going to look like. The distance between here and here is x, and the distance between here and here is y. Now, I already mentioned that this problem is interesting because you get to choose two things. And clearly, one of the things that we're going to choose is x, right? How far away from the edge of the paper we are going to put the dashed lines. But for the second thing that we are going to choose, we can write the whole problem, we can write the volume of the box in terms of the height of the box or in terms of the angle that the side of the box makes with the table, or we can do it in terms of the distance between this point and that point. So when I first saw this problem, I thought that I was going to solve it in terms of the angle. And clearly all of these variables depend on each other, right? Once you pick one between y, h, and theta, you can find the other two because you also have the value of x that you chose. So I thought that I was going to do it in terms of theta, but now that I am actually building the box, I think that my choice is going to be y. My variables are going to be x and y. And the reason for that is because I want to be able to give you instructions on how to actually build the box. And on the flattened piece of paper, y is right there. It's a measurement between a point and another point. But the angle, we can definitely not see here. The angle is something that appears only when we build the box because it's not this angle, okay? It's not this angle on the paper. That would be this angle looking at it like this. But when you take the side of the box, which is in the flattened paper, and you look at it like this, the actual angle between the side of the box and the bottom is a different angle. It's not the one that is flat on the paper. And the height of the box you can't see on this image either for similar reasons. So in order to make it easy to give instructions, the biggest box is going to be the one that has x equals I don't know how many centimeters and y equals this amount of centimeters. It makes it easier to give instructions if these are the variables. But if we happen to need the h and the theta for calculating the volume, you can find them in terms of x and y just like this by looking at this right triangle over there. One of them is Pythagoras and the other one is just the sine inverse. And I would like to take this moment to ask you a question about your intuition. What do you think the answer to this problem is going to be? Do you think that we are going to find a box that looks like this one, that has a bigger volume than the traditional box we found in the first video with 1,092 cubic centimeters, which was obtained by putting the dashed lines 4 centimeters away from the edge of the page? It is completely possible that that same box is going to be the answer to this problem. Our variables that we can choose are x and y, but if we figure out that the best answer is with y equals 0, then that will be the same box. So what do you think it's going to be? What is your intuition telling you? I want you to please put a comment on the video right now saying what you think is going to happen before you watch the rest of the video. And pause the video to do that because I'm about to tell you my intuition. There is an angle and I don't know exactly what the volume formula is going to be like, but it's pretty likely that the sine or the cosine of that angle is going to be part of that formula, even if we're not using theta as a variable, but the sine of theta is y over x. So if there is a y over x in the formula, then that's the sine of theta. And the thing is that functions that have sine and cosine, their maximum points tend to be at the maximum of sine and cosine. And the maximum value for the function sine of theta is when theta is pi over 2. Well, theta is not going to be pi over 2 in this situation, is it? Because then the box would just be flat. But the cosine of theta is also a function that has very well-known maximum points. The maximum of cosine of theta is when theta equals 0. And if theta equals 0 in this situation, we just have the original box. So the first time that I sat down to solve this problem, I was fully expecting the answer to be not interesting. My intuition was telling me that the traditional box would be the optimal box for this situation as well. The next thing that we need to know is how to calculate the volume of a shape like this one. Now, if you turn this thing upside down, it is the bottom of a pyramid that has been cut somewhere here, something like this. The box is this bottom part here. So we can calculate the volume by doing the volume of the big pyramid minus the volume of the pyramid that was removed. But I'm not going to do that because it would be too much work and make the video too long, and there is this formula anyway. Not a particularly well-known formula. I had to go Google it to find it. In order to Google it, though, you do need to know that the shape we're talking about has this weird name, which I am not going to attempt to say. I'm just calling it box because it is the shape of our box. So what a beautiful formula. I am not going to try to prove this formula to you in the video because I don't feel that would add too much to it. I just want you to look at it and see how beautiful it is. Let's compare it to something that we do know, which is the area of a trapezoid. A trapezoid is almost a rectangle, but the two bases are not the same. So instead of doing base times height, you do the height times the average of those bases, a plus b over 2. It's like you're calculating the area of this green rectangle. And you can see that it has the same area as the red trapezoid, right? Because the triangles that are outside cancel with the triangles that are inside. So the idea for the box is that we also want to think of an area that is kind of average in the middle. And by the way, A1 and A2 in this formula means the area of one of the bases and the area of the other base. But it's not just A1 plus A2 over 2, because if you put a rectangle in the middle here, it wouldn't cancel out quite as exactly as those triangles in the trapezoid. Instead, it is A1 plus A2 plus something else divided by 3. So it is still an average of things, but it's an average of 3 things instead of 2 things, which makes sense because this is a 3-dimensional thing instead of a 2-dimensional thing. And the third thing that we are averaging is also a beautiful thing because this is the geometric average of A1 and A2. So it isn't the same unit as the other two things that are being averaged. This is square centimeters. This is centimeter squared times centimeter squared, which is centimeter to the power of 4, but then you take a square root and it's centimeter to the power of 2 again. So 3 things in the same unit, you add them up and divide by 3. This is very beautiful. And I'm not saying that any of these things that I said proves why the formula should be this, because it doesn't at all. I am just trying to explain to you that the formula makes sense. And I'm not showing you the proof. In fact, I haven't even done the proof for myself. I just Googled it. But all of these things that I've just said, you know what just happened? I've memorized it. Now I don't ever have to Google this again because I just know it, because it makes sense to me, even though I haven't seen the proof. And now we are going to apply it to our box. This is the small side of the box, seen from the side like this. But we also have a bigger side of the box, which has a very similar situation, only instead of 21, it's going to be 29 because it is the other dimension of the paper. And this is an extremely complicated looking thing. A1, A2, and H that we need for the volume formula are all just in terms of X and Y, which were our chosen variables. So if you want, you can plug these things into here, but I just don't want to. Instead, this is going to be one of the problems where the math is what we're doing right now. I am not going to even take a derivative by hand at any point in this problem. I am just going to put it into technology. But taking a derivative is just following an algorithm. A machine can do that better than I can. This is doing math, what we've been doing so far. This is what humans are good at. Before I go to the machines, though, I want to think about the domain of my function. This is a conversation that we had when we solved the original problem. The size of the paper is 21 by 29 centimeters. So X can be any number between 0 and 10.5, which is half of 21. Because if you have 10.5 in this corner and another 10.5 on that corner, then you don't have any paper left. So those are the ends of your domain. So I'm adding that information here. And as for y can be anything from 0 if we're just doing the original box, and y can be all the way to x. Well, if y is x, then the box is going to be flat. There will be nothing to fold, so it's going to be less than x. And that is an interesting domain for my two variables because it's not like x has to be between a number and a number, and y has to be between a number and a number as well. No, the domain of y depends on x, which is the other one of the variables. So the thing is that we are talking about two variables. So let's try to put the domain in the coordinate plane with x here and y there as usual. And I'm telling you that x can be any value between 0 and 10.5. So all of the points between the vertical axis and this red line. And y needs to be bigger than 0, so it needs to be above the axis, but it needs to be less than x. So when you look at the line y equals x, in order for the pair of numbers x and y, the point, to be a valid pair of numbers for the domain of our function, y needs to be below this blue line because it needs to be less than x. And on the line, y is equal to x. So if we go down, y is smaller than x. So when you put all of that information together, this yellow triangle is our domain. The yellow triangle is the part of the coordinate plane where x is between 0 and 10.5 and y is between 0 and x. Now, when we go to the technology, we're probably not going to be able to choose to graph a function in this weird domain. We're probably going to give it a rectangle or a square in that case. We can ask the machine to plot our function in the domain where x goes from 0 to 10.5 and y also goes from 0 to 10.5. But we are going to have to keep in mind that that side over there is not actually part of the domain. Maybe that's not going to be a problem because on the line y equals x, if y was equal to x, the box wouldn't fold. So we would have a flat box with volume 0. Whatever our complicated function looks like, it's going to be 0 along this line here. Positive values that make sense for volume inside of the yellow triangle. So I'm thinking that over there, we're probably going to get negative values for volume that don't make sense. So it's maybe not going to be that hard to see in the picture what is the actual domain and what is not. Okay, so let's see what happened when we did that. First of all, I did not substitute things into the big formula by hand. I just typed it exactly as I had written on the paper. The first area is this, the second area is this, the height of the box is this, and then I just typed the volume formula exactly as the new formula that I have memorized today, and the computer did the substituting for me, okay? So the final formula for the volume of the box in terms of the variables x and y looks like this. It looks terrible, it's messy, it's not the kind of expression that a human being wants to deal with just because it's long and it has too many terms. It's not that I don't know how to do this, it's not that I don't know how to take a derivative of this. It's nothing but chain rule and product rule. I just don't want to do that. So I keep mentioning derivatives because, of course, you know that's the direction in which optimization problems go. But before I get there, let's just plot this function and see what it looks like. Okay, so this triangle is the domain of the function exactly like we had talked about before. And the lucky thing that happened here is that the part of the square that is not part of the domain actually isn't appearing in the picture at all. And that's because when I mentioned this before, I didn't realize completely what was going to happen, but the function that we are plotting has this term here with the square root of x squared minus y squared, so that in that part of the picture, when y is bigger than x, then this becomes a square root of a negative number. So that's not even part of the natural domain of the function. That was very lucky because now we just see the domain that we want to see. And why is it colored like a rainbow? The thing is that I have asked the computer to use the colors to represent the value of the function. So the red parts are the biggest values of the function, and then it goes through the rainbow until the purple is the smallest values of the function, because that's 0 when you cut a side of the box that is too big, 10.5. But that is not the best way to look at this function. We are only seeing the domain and some colors. I want to have a vertical axis that is the value of the function, as I usually do. But that's going to make it a three-dimensional picture, right? Because the domain itself has two dimensions, which are x and y. And then I'm going to need a third axis to be the value of the function. So here you can see better the x-axis is going that way, the y-axis is going that way towards the back, and this vertical axis here is the value of the function. You can see all the things with the colors that I was mentioning. The smallest values are here in the bottom, which are purple, and then they go up to blue, green, yellow, and finally red in the top, the biggest values of the function. I had mentioned before that when x and y were the same number, then we would have a flat box because there was nothing left in the corner to fold, so the volume would be 0. So you can see that in this picture as well, because the line y equals x is here, and the value of the function is 0 all along that line. Then it goes up, it goes back down again on the other side when x is 10.5. And the other thing that is interesting to notice here is that when y is equal to 0, the front part of the picture is this curve here. Let me do it in red to stand out more. So if you ignore all the rest of the picture, the three-dimensional part, and you only look at y equals 0, you should see the function that we saw before when we did the original box problem. And that's exactly what this is. The maximum point of that function was the 1092. That was the maximum value of the original box. But the thing is that surprisingly, at least it was surprising to me, because I told you my intuition in the beginning, I thought that 1092 would be the maximum of this problem as well. But it's not, because when you consider the other values of y going further, from this maximum, it keeps going up. The maximum is up here in this red zone, which does not have y equals 0. If you tilt the picture and look at it from the side like this, you can maybe see it even better. The front part of the picture with y equals 0 is here. And from that maximum point, if we go back, we're going to find that maximum point, which looks kind of a lot bigger. So now it's finally time to start talking about derivatives, because from that blue point up there, which is the maximum of our function, we have a function, the volume of the box, that is a function of two variables, x and y. So when you talk about taking derivative of this function, you can be taking the derivative in the variable x or the derivative in the variable y. And although I am not going to do this by hand in this video because the function is too big and clunky, when you have simpler functions like this unrelated example f of x and y that I'm going to show you here, the way to take derivatives like that is that when you're taking the derivative in the variable x, you take derivative of x and treat y as if it was a constant, a number, so nothing is happening here. It's just a number y to the power of 5 that happened to be multiplied by that x to the power of 2. And then when you take the derivative in the variable y, you do the other way around. Now you treat the x as a constant, so nothing is happening to the x squared, and you take the derivative of the y part, which now is 5y to the power of 4. I'm not going to do this part for our volume function. That's what the computer is going to do for me, but I just wanted to tell you what is supposed to happen with those derivatives. At the maximum point that we are looking for, we are used to looking for a derivative equal to 0. But the thing is that if you only look for d dx equal to 0, then this original maximum point here also has that horizontal tangent line going this way. But it's not the point that I'm looking for. I'm looking for the blue point, which also has the derivative in terms of x equal to 0, so it's horizontal going that way. But it's also going to be horizontal going in the direction of y as well. So when you have a function of two variables and you want to find that maximum point, then you have to look for points where both the derivatives are equal to 0 at the same time. And the first step in finding that point is to ask the computer to take the derivative in terms of x and the derivative in terms of y. Now you see why I didn't want to do this by hand, right? Look at this expression. It's horrible. The other one looks just as horrible, and I wouldn't be proving anything to myself if I took the time to do this by hand. Especially because even if I did, the next step was just to make both of these horrible expressions equal to 0 at the same time. It's not the kind of thing that I would be able to do anyway. That's the kind of equation that requires a computer to be doing it numerically, because we don't have algebraic tools to do that, and we don't need them. All that we need here is to ask the computer to solve the system of equations. I want the derivative in x to be 0 at the same time as the derivative in y is equal to 0. And here is the answer. X needs to be 5.5 centimeters. That's a little bigger than the 4 from the original box. And the y needs to be 2.9. So as a rough approximation, 5.5 and 3. So if you want to make the biggest possible box, the way that you have to cut your paper is to put 5.5 centimeters here, which is x, and then 3 centimeters here. This here is the part that you're not going to use. And then you do the same in all 4 corners and fold the box. And the volume of the box that you're going to find when you do that is this number here, 1,271, which, remember, we are comparing to 1,092 from the other box. So that is considerably bigger. It's approximately 20% bigger. I've said this before in other videos, and I think I'm going to keep saying this forever, but every time I find a problem that I hadn't seen before and that's really, really interesting, I feel like that was the last interesting problem that remained to be found. I was teaching math for 15 years before I ever thought of solving this problem. But surely now this is over, right? There can't be a better box than this one to be folded out of a sheet of paper, right? Can you think of a better box?